Okay, good morning, and let's get ready to click. We have a bunch of things to talk about. In addition to homework and our astronomy topics for today, I do have a few announcements concerning this and that. First of all, Hurricane Irma, it's kind of far away right now. It's hard to tell what's going to happen. But Thursday I will give you a plan. I have to talk with my BOSS in the physics department, and he has to talk with his BOSS upstairs, the Dean of Sciences, and he has to talk with his BOSS, the Provost, and then the Provost has to talk with the BOSS, President Hill. So it's kind of coordinate things. But Thursday I'll let you know, because if it does hit us, it looks like it's going to hit us next Monday, right before our first exam. All right, so on the 12th. So we may have to, but hopefully, it's still a little early. It might, I hate to, bring misfortune down on anybody, but I'd rather for it to hit Cuba and lose a little steam and before it comes up our way. Anyways, here's a picture. This is from the Ocean Prediction Center from NOAA. Here's Orlando down here where the black arrow is. And then right down here at the bottom of the picture is where Irma is. And max winds 120 knots, et cetera, et cetera. That's from the Ocean Prediction Center. You can jot down this address if you like looking at data. This is a real weather map here. Now, a couple other good ones that I like, especially for those of you that haven't been to, a lot of you are not from Florida. So if you're from Florida and you've been here for a few years, you already know all the good hurricane sites. But if you're not, here's a couple nice ones. Here's the National Hurricane Center. That's also NOAA. Ocean Prediction Center is nice. And both of those link to satellite imagery. So you can look at infrared images of the clouds, from satellites. Visible light, you could see the actual, what it would look like from the space shuttle, for instance. Although they're black and white images, they're not color. Here's another one. It's a private website, Weather Underground. And the thing I like about this website is you can see all the computer models. The National Hurricane Center doesn't make the hurricane models easy to track down and view, but Weather Underground does it. So if you jot those down and get your mental mindset. By the way, raise your hand if your hometown is not here in Florida. Okay, that's a good number of you. Raise your hand if your hometown is like Jacksonville or Tallahassee or somewhere up in North Florida. It's a good bunch of yous. All right. Now, and this is not astronomy. This is just me talking to you guys as human being to human being. And that is, if you stay here at UCF, they're not going to evacuate UCF. They may evacuate the dorms if you're staying here in the dorms. But what they'll do is they'll bring you into buildings like this. And so you'll bring blankets, and it'll be, like a camp out, like a huge sleepover, all right? But these buildings are pretty much bomb-proof. Matter of fact, the Mathematical Sciences building actually is built to withstand a nearby nuclear detonation. That's why it doesn't have any windows. That was built back in the 60s. And like a lot of technical buildings back then, they actually were bomb-proof. Anyway, so if you are here on campus, tell your parents you're going to be safe. You might not get a shower as much as you want. You'll have food. And you know what else? The internet on campus will be working. I guarantee it. They might shut down the Wi-Fi. I don't know what they'll do with that because we have a lot of Wi-Fi. Last time we had a big thing, hitting Orlando, which is definitely at risk for Irma. The last time we had a direct hit on Orlando was Charlie back in 2004. Now, most of you guys were little shrimpy kids at that time. But Charlie, web courses was running the whole time. The internet was running the whole time. So you could actually do homework as the weather is blazing through. Not that you're going to want to, but you will be able to. But what that also means is you might be, if they keep the wireless access going, like WPA2 or something like that, you might be able to contact the MOM at home, so she doesn't worry about her little baby up in Orlando. So in other words, if you're too far away to go home to help out your parents. Now, a lot of you guys are going to bust out of here. It's not going to hit us till maybe Sunday or Monday. So if we'll have class. We should have normal classes Thursday, but they might close classes Friday. So if you guys bust out of here and head down to Fort Lauderdale or what's that little town by the West Palm Beach, anywhere out there by, what's the name of that big lake? It's escaping me right now. Okeechobee. Yeah. Now what's that? Clewiston. If you have to head back to Clewiston, to help out your parents and whatnot, that's going to be good. But if you are here, you will be safe. And you probably will have to eat Army meals ready to eat or anything like that. But you won't have cafeteria service either. So you know what you should do if you know you're going to stay here. I mean, if your hometown is like Missouri, so you're not going to fly back. Make sure you lay in a supply of Pringles and hide them until the storm hits. Don't let your roommate know about them. Okay, and granola bars. Make sure you have plenty of Slim Jims and all that kind of stuff. Because but they'll put you in buildings like this, and you'll be perfectly fine, and so it won't be a problem. And campus will come back as soon as the storm is through. Campus will be up and running really fast, although there might be trees down and stuff, but they'll get those cleared out pretty quickly. Question?
So we're for sure going to be hit by Irma?
We're not for sure, but I'm saying by Thursday we'll know. It's still a few days away before we'll know for sure. It's looking like it right now, but I was listening to Channel 9 Eyewitness News and this morning, and they were thinking it might. It's still a possibility for it to stay south and blaze over Cuba before it turns north. And if it does that, it's going to lose some steam. And then, of course, depending on where it hits Florida, if it goes, like right now, the track goes right over the Florida Keys and then straight up the pipe, straight up the peninsula. Now, when it does that, that's actually, it deluges the Everglades, and then Lake Okeechobee and Clewiston, and then on up, and then it's going to defibrillate itself a little bit, hopefully quite a bit by the time it gets to Orlando. But you never know. But if it comes straight in from the west or from the east, then it's going to be a lot stronger. So we don't know exactly, but if by Thursday we'll know, we'll have a good idea, and you guys will, same as like, what was that last year? Matthew? So it'll be similar to Matthew. Matthew was looking pretty grim, but at the last minute, I was watching, I predicted exactly what Matthew did. Kind of stayed. And you guys, an extra 10 miles off the coast for Matthew made a huge difference here in Orlando. Yeah, it hit. There's nothing to do about that. because they're right up there by the ocean, and they get the storm surge and stuff. But here in Orlando, an extra 10, 15 miles, which was what I was predicting, it looked like, and it was true, made a huge difference here in Orlando, But Charlie tore the place apart. It was grim. But Thursday we'll have plans in place. We'll talk more about it then. But I don't want anybody to be afraid. And if if the Mamasaurus calls you and she's worried, and that's what Mamasauruses are supposed to do, just tell them, no, Dr. B said that we're going to be safe as a bug in a rug. And she'll say, who's Dr. B? But anyways, you should be good. All right, now a couple other things. We're going to have some homework tonight. It's not that big of an emergency that we start canceling homework. Homework 2, I decided to just have a nice weekend. But homework 3 will have reading and stuff in chapter 3 and about Kepler's laws of motion for planets and stuff. And actually, I think a little chapter 2 action. And what I'll try to do is get that all written up and fished up for you right after this class. Should be ready to roll about noon or so. All right. And that'll help you prepare for lecture carefully on Thursday. And as I mentioned, our clicker questions are going to interrogate your knowledge of the readings. All right. So you want to, if I give an assignment, then there's going to be at least a few questions, clicker questions, the following lecture from the reading, and we're about to do one. So hopefully you did the readings from last week. On the topic of clicking, today is the first official day of class participation with iClicker 2. And so what I want you to do, if you haven't started your clicker, turn it on now. Press the power button until if you're already on frequency DD, you're good. But if you're not, if this is the first time using it in my class, hold the power button down for a couple seconds until the little rectangle flashes, and then type in DD, delta, delta. And then you'll get an OK, and then it'll say go nitro. And then that means you're talking to my computer, because you can click to your heart's content on frequency DD, but if you're not also registered through web courses, not through iClicker.com, that's some other class maybe, but not our class. Our class, you have to register through web courses. Then I will know that your clicking is you. This thing will be picking you up, but if it doesn't know that clicker AF739B is you, then I don't know it's you. All right, so that's why you have to register in web courses. And a few of you guys came up before class and said, hey, Dr. B, am I registered and stuff? And the way that I do that is I synchronize the roster after each clicking session, and then I'll be able to see. And if we dismiss a few minutes early, we'll try to do that at the end of class today. All right, so I'll be able to see. So, but today's the first day for official clicking, so we don't get any bonus points for today. You just get regular participation pointage. All right. And speaking of that, let's try a question. Raise your hand if you got the Go Nitro. All right, good. Question number 1. Go ahead and start. Okay. And you can go ahead and start voting. Read very carefully. All right, I can see you starting to vote. Click out the histogram, please. We'll see how this is. It's not all frozen into one answer. There's a little bit of uncertainty. Yeah. Now, you said you're a physics major?
Engineering.
Engineering major? So you don't take quantum mechanics?
No, I don't have to.
Yeah, but you're astronomy major? Or astronomy minor?
Yeah.
Okay. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Go ahead and switch to this. All right, here's the distribution of answers. And, okay, switch back. You can see that we have a distribution. In other words, the majority of class is not just voting for, in fact, nothing here is over 50%. All right, so the correct answer is actually this one. And if you, yeah, so go down to Rio de Janeiro in Brazil. That's 7,000 kilometers from us. So if the sun were the size of a basketball, then the nearest star, Proxima Centauri, also known as Alpha Centauri C. Alpha Centauri is a group of 3 stars, and right now, they're all mutually orbiting each other. And right now, Alpha Centauri C is closest to us. Yeah, it's actually 4.24 light years away, but on this scale, the basketball scale, it would actually be 7,000 kilometers. Now, I made some maps for you, and I just want you to eyeball this. Eyeball this one. This one shows everything on the red line in this map is 7,000 kilometers. Now, this is like a lot of maps. It's distorted at the North Pole and the South Pole. But around Orlando, it's pretty good. All right? And so this red line, everything between Orlando and the red line is 7,000 kilometers or less. So Rio de Janeiro, where they had, isn't that where they had the Olympics last summer? Yeah. And then here's Santiago, Chile, over here. That's 7,000 kilometers. Did you know that here's something cool. The Pacific coast of Chile is east of us. The Pacific coast of Chile, the west coast of Chile, is east of us. We'd have to fly slightly east to get there. You know, you always think, oh, Pacific, fly west, go west. Not down there in South America. All right, here's another place, Dakar, Senegal, right on the coast of Senegal. That's where a lot of flights between South America and Africa and Europe, they land there in Dakar and gas up their jets. Famous airport there. Madrid, yeah. Madrid's just about 7,000 miles. London, England, yeah. About 7,000, or not 7,000 miles, 7,000 kilometers. All right? And all the way back over here, Nome, Alaska, also about 7,000 kilometers. Now, here's another one. You might be able to sketch this one in. This is what we call an azimuthal map centered on Orlando. Now, you can see that the center of all these, they look like spokes of a bicycle wheel. The center of them is Orlando. The edge of this map is 7,000 kilometers from Orlando International, MCO. Right? Now, this one you might be able to map. So go ahead and try to draw, make a little sketch of North America inside of a circle, the upper half of the circle, and Florida's right in the middle, and put a little dot there for Orlando, kind of in the middle of the Florida. And then, like the shoulder and chest of South America, and then just a little bit of Africa. Don't worry about the edges, because I've got the edges identified. The arrow up there right now is set for England, London, England. So get your circle, get your North America, and then right up there, it's almost 45 degrees. That's London. Okay, so if you headed about 45 degrees from Orlando and just kept on going, that's where you'd get to, London. All right. Now here's Madrid, a little bit south of there, in Spain. Okay, so at this part of the map, south is clockwise. All right, so there's Spain. Now down here is Dakar. And actually, Dakar is right between us and the Cape Verde Islands. And the Cape Verde Islands are important during hurricane season. That's where they start. Anyways, that's Dakar. Dakar is about, in the direction of the Cape Verde Islands, is about 7,000 kilometers. And on this graph, it's about 3 o'clock. Wait a minute, is that 3? Yeah, that's 3. 3 o'clock. All right. Now, Rio's down here at about, I don't know, 5 o'clock. All right, there's Rio. And then Santiago de Chile is up here. It's about 5:30. Okay. And then Nome, Alaska, 7,000 kilometers, all the way up here, from the South Pacific all the way up to the North Pacific. So here's the upshot. If the sun is a basketball, then the Earth is an apple seed, about 30 meters away, and Alpha Centauri C would be another, well, it would be a little bit smaller, maybe a volleyball, or maybe, what's smaller than a volleyball but bigger than a softball? Let's call it a softball. Alpha Centauri C is a smaller star. It's not as big as Alpha Centauri A. But anyways, Alpha Centauri C would be up there in Alaska. Like maybe a little smaller than a basketball, maybe a little bigger than a softball. So think about that. You're trying to see that thing, and we can see it. You can't naked eye Alpha Centauri C, but not too big of a telescope you can get it. And Alpha Centauri A, if you're in the right part of the Earth, and especially the southern hemisphere, yeah, you can eyeball it. So as a jet flies, that's how far away it would be. But let me ask you a question. What's the problem with using the Earth and distances computed on the surface of the Earth as a jet flies from Orlando? What's the problem with that? Raise your hand if you, what do you think the problem with that is? Yeah, it's on a curved surface. It's not, a photon of light from Alpha Centauri C to Earth, to your eyeball, to your telescope, just straight line. Okay, so these are not straight lines. So it's actually, if you took a straight line from Orlando, like one of the runways and just shone a laser beam down the runway, 7,000 kilometers would be, out there way above the surface of the Earth if it goes straight. But anyway, that proportion is described in section 1.6. And let me draw your attention to figure 2. Section 1.6, we're going to finish that today with our comments on that, and then we're going to start dipping into chapter 2. And we'll talk about zodiac and ecliptic and constellations and stuff. And then chapter 3, Kepler's 3 laws. But section 1.6, the tour of the universe, figure 2 is pretty important. We're going to look at that in a second. But this whole basketball proportion, I don't really like it a whole lot, but it's legit. I mean, it's a normal thing to do. Astronomical distances and then the smallness of an atom and the smallness of the nucleus compared to the electron orbital distances is another one where it's just very hard to fathom how incredibly much a distance there is between the electron and the nucleus, between Earth and the nearest star. And that's just the nearest star. Forget about galaxies. Now I've got a whole lecture about the Andromeda galaxy. That's our nearest spiral galaxy neighbor. But for now, this is a good one to look at. Now, here's figure 2. There's the Earth. Now, I'm bringing in the moon from figure 2. It's just kind of sliding off to the left here, and it's taking its sweet time. There it is. There's the moon. All right, now make a note in your notes, figure 2 of section 1.6. And here it is. Here it is in one shot. Okay? I shrank it down so that you can see all in one, all in one glance. Yeah, figure 2. These are the true proportions of Earth and the Moon for size and for distance, and it is significant. I mean, you put your thumb up, and for most people, your thumb will cover up the full moon pretty much. All right. So, and the sun as well. I mean, the sun and the moon are about one thumb worth, unless you have really skinny thumbs. But anyways, one thumb worth for the moon. It seems pretty close, but this is the true proportion of it. All right, let's do some more comments on chapter 1:6. Okay, first comment, or the first comment for today, is a quote. We call the average Earth-Sun distance an astronomical unit, and the symbol for that, or the abbreviation, is AU. Because in the early days of astronomy, it was the most important measuring standard. And we'll talk more about that. But 93 million miles, you probably heard that a zillion times since you were in like third grade and stuff. 500 light seconds, that's what we learned last week. All right, that's what I prefer to think of the distance as. And as a side note to this, it says in the early days of astronomy. And so what that means is they had to do a lot of calculations really in proportions. All right. Now, by the time of Sir Isaac Newton, they had a good idea of the diameter of Earth and the distance to the moon in miles and feet, and a fairly good distance to the sun and to the planets and stuff, because you can work it all out in terms of the radius of Earth. So if you know the size of the Earth, you can kind of work it out. So they had that. But to get to another star, to triangulate a distance to the nearest star was very difficult. Now, they first did that back in 1838. So that's 179 years ago. A fellow named Friedrich Bessel from Germany. He triangulated a star called 61 Cygni. Now, Cygni indicates that this star is in the constellation Cygnus, Cygnus, Cygnus the Swan, which is a summer constellation. Also has our first identified black hole is known as Cygnus X1. It's a source of X-rays. But anyways, Cygnus is a summer constellation in the northern hemisphere, and he was able to bag triangulate the distance back in 1838. Now, once that happened, then you can start really get an idea of other distances and so forth. And he was the first one to do it, 10.3 light years. Okay, and eventually they got triangulation for other stars. And we have actual spacecraft in orbit. The Hipparcos satellite, which is now out of commission, and then the Gaia satellite orbiting Earth. All they do is triangulate on stars. And they have an ultra precise aiming system and basically an ultra precise protractor. I mean, if you can get your angles, from observing in June and then observing the same star in December, that you'll have to tilt your telescope slightly different angles, and that allows you to triangulate. do a little bit of Pythagorean theorem. But for a long time we had to just say, oh, it's so many AUs, so many astronomical units. But now we can figure it out in light years and stuff like that. Okay, a few more comments. Another one that I did not like seeing this. A planet is defined as, and then the authors write this sentence, and I'm thinking to myself, no, this is not right. Not so fast, you guys. The planet was redefined in 2006 by the International Astronomical Union. That's where, in other words, that was the famous meeting in Prague, in the Czech Republic, where Pluto got demoted, which I mentioned last week. Here's a nice little link, a URL, and I'll put that in the Homework 3 HQ page. Don't worry about writing it down. But you can read more about the true definition of a planet and the accompanying sub-definition of a dwarf planet and what they call Plutoids or trans-Neptunian objects, TNO. It's kind of cool. Anyways, that URL will be linked in the Homework headquarters page. Another quote. This one's kind of cool, and we're going to spend some time with this one. If planets were much further away, the tiny amount of light they reflect would not be visible to us. All right? So for instance, Uranus, Neptune, and Pluto are so far away, we can't see them with the naked eye. All right? But we can see Saturn is close enough to see it with the naked eye. On a clear night, Jupiter, Mars, Venus, Mercury, they're all close enough. All right? Now, here's the cool thing. Astronomy Picture of the Day and NASA in general have a bunch of images of Earth and the Moon from Mars's viewpoint. And so what I want to do is view with you now some of the latest images from the rover called Curiosity, which is the newest one that they have up there on the, roaming around on the surface of Mars. So let's take a look at some Mars images. And actually, let's here's the Curiosity. Just eyeball this. There's some men in the picture there wearing suits. What everyday object would you say is maybe about the same size as this rover? Take a look at it. What everyday object? What do you think? Yeah, maybe a car. You know what I wrote down in my notes? Pickup truck. Yeah. You can see it only because it's a little taller than a regular car. But could you imagine zipping around Orlando in one of those babies? That's like millions of dollars for that thing. So you wouldn't want to do it. You would never get permission. But if you could secretly do it at night, it'd be kind of cool. Anyways, so that's the size of it. Now here's a picture, and you may think to yourself, Dr. B, this photo proves that there are aliens that work for NASA and they live on the planet Mars. Because how did they take this picture? Look at that. It's not it's not like a selfie, you see the guy's arm up here, coming out of the picture. So aliens, man. Or some clever dudes out in Pasadena at the Jet Propulsion Lab, which is, I think, what's the HQ for this rover. What they do, see that big camera up there on top? And there's a bunch of other cameras, and basically they do have a selfie stick on that thing so they could take pictures of the machine. And what they did is they took a bunch of selfies and then they kind of stitched them all together so that it looks like it's a friendly alien taking the picture. But that's a legit image of the Curiosity rover. So that's a pickup truck. Oh, look at those rocks. All right, everybody look at those rocks. Look at the surface. Look at that mountain off in the upper left. Now, raise your hand if you've ever been a place where the ground resembles that. I have. Okay, with the rainbow colored shirt, where have you been? Where was it? New Jersey? What? Where in New Jersey? I grew up in Jersey. Is this like a trick or some kind of radical therapy or where in Jersey did you see the ground that looks like that? Oh, you know what? I know what you're talking about. There's some red shale, big formations of red shale. But of course New Jersey's got trees and stuff. You know, from this one's horizon. Who's ever been in like a deserty area that looks like that? Okay, with the blue shirt, where was it? Grand Canyon. Who's been in the Grand Canyon? Are there places in the Grand Canyon that look like that? I've never been, so I believe you. Who else? Where have you been? Desert California. Like they got Death Valley and the Mojave Desert and stuff. Me, southeast Montana, and it was kind of cool, almost down into Wyoming, because it was pretty close to where a lot of the astronauts trained for the Apollo mission. You know, they trained in a bunch of places, but middle of Wyoming they did. And where I was, and you may have noticed it down there in California or over in the Grand Canyon, huge numbers of fossils. I mean, you think you're walking on sand. It's not. It's fossils. You know, little tiny crustaceans and stuff. It's pretty cool. So anyways, that's what and it was there back at the end of 24, or beginning of 2014. I should have looked up where it is today. All right, now here's now just eyeball this. This is near where it is, where it was at the time of the pictures. This is a place called Dingo Gap. I have no idea why they call it Dingo Gap. Now this is from a fisheye wide angle lens. Okay, so it makes everything curved. Okay, but what NASA does, they take that data. This is like a raw image. It's black and white. And then they process it. You know, they reprogram each pixel and you kind of flatten it out like this. So there's the same gap. And also colors. And they've got some little rulers. NASA put those on, not that friendly alien that's working for us up there. But that's Dingo Gap. All right. And boy, there's tons of places out west that look like that. Tons. I mean, all right, so here's a close-up. So this little gap, and then see there's a big sand dune back there on the other side of the gap. And here's the Curiosity tracks having gone through the gap. And you see those mountains in the background. Now, I told you that this was about seeing Earth from Mars, right? So this is all this stuff is during the day. Right? This is what it looks like during the day, right? But at night, can you cut all the lights, please, Trish? All right, we're going to try to emphasize that's what it looks like at night. Do you see the Earth? I can see it. because I know where to look. Can you see it, Trish?
Yeah.
Go point, Trish, go point to it. Let Trish point to it. My trusty TA. Right there. See that little, thank you, Trish. See that little white dot up there? That's the Earth. If you're up there in Mars with Curiosity and the alien that's working for NASA, they're, just chilling and stuff. Yeah, man, that's where I grew up over there, New Jersey. See that little... All right, there it is. It's a little bit bigger picture. But that looked at Mars, and we're going to go in depth on the planets, in the next couple of weeks. Mars has an atmosphere, and that looks like a lot of atmosphere. That looks like, a night, like way up in the mountains out west, out in the Rockies. So, now here's a close-up. This is the way the close-up looks. All right, now I want you to sketch this one. Okay, you've got the Earth up here, upper left. All right, and you've got the moon down below. Now that's what that little white, you can turn on the lights now, the fluorescence. Great. Okay, now this one will be easier to see from your seats. All right, now that little white dot that Tricia pointed out is this pair of, it's actually two blips. You couldn't see the moon in the original image, but here they are in close-up. Now, I want you to draw a line like that to signify the terminator. That's the edge of the shadow on the dark side of Earth. All right? And it's important. Now, there's a terminator on the moon as well, so draw that in. And it's not, these aren't perfect half moon and half Earth phases, but it's fairly close to half moon and half Earth from Mars. That's kind of cool to think about. Right? Now, that terminator line from the north to the south for both is important because perpendicular to that is a line that goes straight to the sun. So draw a line perpendicular to the middle of that terminator. So that's my green, my thick green, greenish yellow line here.
Joan or amazing, lovely Winifred Bruckner.
That's the BOSS. Hold on a second. Joan, I'm in the middle of a lecture. She hung up on me. Fine. Anyway, she just forgot. Anyway, yeah, so that line, it's perpendicular to the red one, and it goes straight to the sun. Now, the sun is way, way out of the picture here, but it's in that direction. Now, the same thing is true for the moon. You might be able to draw it in, but I'm not going to. There's, similar line pointing back to the sun. And it basically goes from the terminator over the day side of Earth, from the terminator over the day side of the moon, and towards the sun. All right, so kind of eyeball that in on your sketch. Now, the reason I'm bringing that up is the following. The shadow of the moon will be in the opposite direction. Shadow of the Earth and the shadow of the moon will be like this. Here's the shadow of the moon. Now, I made it in light blue so you could see it. All right, but actually it would be the absence of sunlight. And it's kind of a cone shape. It's not perfectly straight back. I've exaggerated it a little bit. But it definitely reaches back to the planet Earth. Now, the problem with this is, or not, it's not a problem, but that shadow is not causing an eclipse on the surface of Earth because it undershoots. So make a note of that. The shadow of the moon it's always possible to get a shadow of the moon pointed towards Earth, but at certain times of the year, certain parts of its orbit, it's going to undershoot. Because the moon's orbit is tilted with respect to Earth's orbit around the sun. Okay? So make a note of that. The moon's tilt, so if the Earth is on the orbit of the Earth around the sun is like a plate on a table, then the motion of the moon around the Earth dips above the table and then curves below the table and then back above the table at just a few degrees of slant, and you can see it here in this image, so it's kind of cool. All right, so this shadow, it's always there. The sun, the moon's always going to block the sunlight, behind it or outward from the sun and behind the moon. Okay, the dark side of the moon. But it doesn't always intersect the Earth because the Earth's orbit. So draw a dashed line between the center of the moon and the center of Earth, and I made my kind of light blue here, just to signify kind of an easy sketch that this is where the moon orbit. It's on this orbital plane. All right. And so the direction of the sun is at an angle to that. And so for that reason, our planet doesn't always catch that shadow. But it did 2 weeks ago. Is that when it was? Yeah, it was like the first day of classes. Hey, I forgot to ask you, how many people here viewed the eclipse on campus? It's kind of cool. That's good. All right, let's keep going. All right, so that's something. Now, these are all NASA images. So you can look them up in APOD and NASA.gov and stuff like that. All right, now, here's another quote from section 1.6. The sun is somewhat less than 30,000 light years from the center of the galaxy, the Milky Way galaxy, in a location with not much to distinguish it. Now, that's kind of an ambiguous sentence, and now that I look at it, I guess they're talking about the location of the Earth, because they can't be talking about the center of the galaxy. The center of the galaxy is definitely not indistinguishable. There's plenty of stuff happening at the center of our galaxy. For instance, there's a gigantic black hole at the center of the Milky Way galaxy. It's millions of times more kilograms of mass than our star, the sun. So it's really big. Now, we've seen other black holes nearby, like Cygnus X1, that is a few times the mass of the sun, okay, depending on the estimates that you make of it. But it's not a million times the mass of the sun. The big black holes are in the center of galaxies, and some astronomers and physicists think that every galaxy of any size has a black hole at the center. We're trying to figure that out. But definitely there's one. And this image here is from a famous article in 2002 where they first mapped out the orbit of a star. Now, SGR A star, it's Sagittarius A star. SGR stands for Sagittarius. So SGR A star or Sagittarius A star is a black hole. And that is right over here where this, let me get my cursor over here. Right over here where this circle with a plus in the middle of it is. Okay? Now, they mapped out another star called S2 from 1992 up here in the upper left of this ellipse, and they observed it 94, 96, here's 97, 99, 2000, 2001, 2002, and right down here, look at this. This is all 2002. Right now, out here, look at this. On this part of the ellipse, out here on this extreme far part of the ellipse, 90, 92, 94, 95, 96, to go across this upper few degrees of turning on the ellipse up here, that's like 3 years worth. All right? Now, visually, look at the opposite end down here. Similar amount. Dude, that's like 1 year down here. Why is that? It's because the star is closer to the black hole. Gravity is stronger. It's accelerating. It's going faster when it's down close. And it's going slower out here where it's far away. Gravity's weaker. All right? And you may say to yourself, hey, Dr. B, I thought everything gets sucked into a black hole. No. If you're far enough, if you're outside the event horizon, you can do a perfectly fine, you can do a perfectly fine orbit like this. There's no problem with that. You know, but you know, when you're far away, it's going to be kind of slow. And we see, you know, most of our planets are really close to circular orbits. Okay. Mars is a little bit elliptical. Mercury is a little bit. We can measure them. We can see it. We can observe the ellipticity. But they're still pretty close to perfect circles. And Earth is really close. But comets have orbits like this. Asteroids, some asteroids have orbits like this. And, you know, where you come in really close and you really go fast. And then you have, you know, a real pokey region out there where you just kind of poke it along. Yeah. So yeah, the center of our galaxy is definitely an interesting place. And it has plenty to distinguish it. And let me just make a final note here. It's not in the outline, but you can write it down as item C. This image came from looking at infrared, using an infrared telescope. Because if you, and you know that if you read section 1.6, you'll know that visible light, there's so much in the way, stars and things, between us and the center of the galaxy, it's hard to see visible light, but we definitely can see infrared. And it's tricky and hard to do, but we can see it. So this is infrared. Now, another thing that I want to go with you, I'm just going to give you an IQ test question here, one more clicker question. And here it is. Go ahead and start the question, please. Okay, you're on frequency DD. If you don't have the Go Nitro message, if it says no bass, then hold the power button down for 2 seconds until the rectangle flashes. And then type in DD. And then you'll get the Go Nitro message and a check mark, and you'll be able to vote. So this one's A and B, true or false. And hey, you guys, on exam 1, whenever we take it, hopefully next Tuesday, a week from today, we'll have some true and false questions on there. So, you know, we'll have some matching, we'll have some true and false, regular multiple choice. 10 seconds. Is space mostly empty, true or false? 5, 4, 3, 2, 1, 0. Ching. Go ahead and show that. Uh-oh. We got some splaining to do. Go ahead and switch back, please. Thank you. Because that is false. Space is not, it may look empty, but over the vastness of space, we can't see down into the middle of our own galaxy. Because there's all kinds of dust and gas that absorb light and refract it and reflect it and stuff. So let me go through here. Here's item 6. The space between the stars is not completely empty. It contains a sparse distribution of gas, mostly the simplest element, hydrogen, intermixed with tiny solid particles that we call interstellar dust. And interstellar dust is a problem. Especially if you're trying to look along the long axis of a galaxy, which is what we're doing. When we're about 2/3 of the way out from the center of the Milky Way galaxy. So if we want to look back towards the center, we're trying to look through a lot of dust. But infrared goes through the dust pretty well. But visible light, not so much. All right? Now, how do we know that? Well, we know the quantum fingerprints of hydrogen and helium. Neon, we actually looked at that 2 Tuesdays ago. And we know how to spot the fingerprints of all kinds of substances. Now go ahead and write down this word, pyroxene. And pyroxene is a chemical name, and you may be saying to yourself, Dr. B, this is very nice, pyroxene, but I find it a little boring. But actually, pyroxene is kind of an interesting, you know what another name for pyroxene is? Jade. The beautiful gemstone jade is pyroxene, a form of pyroxene. There's the chemical formula, sodium aluminum silicate. Okay? Is that fantastic or what? We can look out in space. You see plenty of hydrogen, and that's kind of cool in itself. A lot of helium. We can see oxygen. We see water molecules. Did you know that we can see sugar molecules in space? Pyroxene. We can see it. It's not everywhere, but we've seen it. And if you think about it, pyroxene is, look at that chemical formula, NaAlSi2O6. Okay? And here on Earth, we got a bunch of silicon and oxygen are the two most abundant elements in the crust of the Earth. A lot of our rocks, silicon and oxygen. But we see pyroxenes like this out in space. So what that means is that you're looking at debris of planets for which the star was born, and then the planets formed, and then the planets came to an end and were destroyed in some way and left this dust behind called pyroxene. It's truly amazing, if you think about it. And here's something else I want you to think about. And this is almost a biology question. And some of you that have, raise your hand if you've had biology class of any kind here at UCF. Okay. Glucose, sugar molecule. Fructose, sugar molecule. Sucrose, sugar molecule. Anything ose, I think, is a sugar molecule. Sugar molecules, a bunch of carbons, a bunch of hydrogens, a bunch of oxygens, right? They have a particular structure. Now, if you have a molecule like CO2, it's got a carbon and then two oxygens, and they all line up, pretty much. Now, hydrogen, H2O, is an oxygen and two hydrogens, and they form kind of a V-shaped, okay? But something complex like a sugar can have a bunch of V-shapes, okay? And when you look at the shape of the sugar molecules, which you can figure out using diffraction, they have a handedness, right? You know, like DNA. DNA, the spiral structure of DNA, has a handedness, what we call chirality. Let me spell that word for you. chirality, chirality. Let me spell it again. chirality. It comes from the Greek word for hand. Chirality, the handedness. So DNA, it spirals upward in a certain, manner instead of the opposite manner. So when you go clockwise in the DNA, it goes in this direction. When you go counterclockwise, you go the opposite direction, down the spiral. Okay, depending on how you look at the spiral. Okay, so a molecule like DNA has handedness. Sugar molecules have handedness. And here's something cool. All sugar molecules form from living things that are alive. Plants, animals, algae. I don't know if algae make sugar. I guess they make carbohydrates. So all sugars from living sources. No matter where we look, they all have the same handedness. I think they're left-handed. You could look it up. They're either all left-handed. Do you happen to know? Do you know if it's... No. They're either all left-handed or they're all right-handed. All sugars... So we can make the other kind of sugar, the opposite chirality. We can make it in the lab, but nature doesn't make it that way. Why is that? And here's the interesting thing, in addition to seeing jade out there in the universe, in the dust, the stardust, the debris of old stars and planets, we can see sugar molecules, and guess what? The same handedness as the stuff that's alive here on Earth. And nobody knows why that is. But a lot of people would like to know. So there is a huge amount of interesting things, not just this beautiful gemstone jade. Now, your homework assignment, we're going to dismiss a little early today. And for those of you that want to check your clickers, you can come on up. Homework number 3, reading assignment. Follow-up iClicker questions Thursday. I'll have ready for you about noon in web courses. It's already up, but it's under construction. I'll finish constructing it in about an hour. You're dismissed. See you on Thursday.